Hi, welcome back to another exciting Math 112 lecture. I really like this topic today. Today we are going to talk about, I like all of trig, but today we're going to talk about a really useful notion, and that is inverse trigonometric functions. So what we're doing here is we're building up to the ability to solve equations involving trig functions. And in order to do that, we have to have inverses. So let's talk about what an inverse function is, and let's revisit our periodic table. Or not our periodic table, sorry, wrong class. I teach chemistry too sometimes. Our unit circle, but part of the reason I made that slip is because the unit circle is kind of like the periodic table of trigonometry, right? The unit circle gives us a whole bunch of information all crammed into one tiny little space. And there, this is what I need. So what do we have here? Well, we've got some key angles here in both degrees and radians, right? We've also got, though, the coordinates of the points whose radii make that angle with the positive x-axis. Yes? But more importantly, we need to remember that these coordinates represent cosine and sine. So what that means is, looking at this, we can find, for example, the sine whose angle is 1/2. Or another way of saying that is, let's solve the equation sine of theta equals 1/2. What that means is find all angles that have a sine equal to 1/2. Or in the words of our unit circle, find all of the angles whose radii lead to a point with a y-coordinate of 1/2. So between 0 and 2 pi, that would be pi over 6, 5 pi over 6. But what if we keep going around? What if we go again? So I got this one, and I got this one. But there's another angle that if I go all the way around and come back, I get back to this same angle that still has sine of 30 degrees. And that would be 13 pi over 6. You get the idea. We could keep going around and around and around. There really is no for all solutions here, right? Unless we write a series. But what I want you to understand is how I got to these two angles. So what I did was I found the angle that had a y-coordinate of 1/2, because the y-coordinate is the sine. So what if I want to find the angles whose cosine is square root 3 over 2? Well, that would be 120 degrees and 60 degrees. Or 2 pi over 3 radians and pi over 3 radians. Let's make this a little bit more complicated. Let's suppose I need to solve something a little bit more tricky. let's suppose I need to solve the formula, or the, equation for cosine of theta plus 3 square root 3 equals square root 3. What am I going to do? Well, the first thing I want to do is isolate my trigonometric function. So let's subtract 3 square root 3 from both sides. So we get 4 cosine theta equals negative 2 square root 3. Divide through by 4. And we're looking for the angles whose cosine are negative root 3 over 2. And if we consult our unit circle, we will see that we've got, now cosine is the x coordinate, so we've got a cosine of root 3 over 2 here, and a cosine of negative root 3 over 2 here. So the angles are 5 pi over 6 and 7 pi over 6 radians, or 150 degrees and 210 degrees. Okay? All right. We want to be a little careful. Sometimes we remember that we've been working with non-standard periods in previous sections, right? Things where we had what I call an internal multiplier. So let's look at how to solve the equation sine of 3 theta equals 1/2. Well, I'm still looking for angles whose sine is 1/2. So, but this time I'm gonna, so that would be pi over 6 radians and 5 pi over 6 radians. What that means then is that 3 theta equals pi over 6, or 3 theta, let me put that down in the row. Or 3 theta equals 5 pi over 6. Now all I need to do is solve that for theta. So theta equals pi over 18, or theta equals 5 pi over 18. And I'm sorry, but my buddy came to work with me today, and he needs to be confined a little bit, so. This is my buddy, Sprout. Sprout needs to settle down. Take a nap. All right, sorry about that. You get the idea? So let's take another example. Let's figure out, so let's say that we've been told, or we know, that the temperature over a day can be described by this function, T of H, equal to negative 10 times the sine of pi over 12H plus 50, where H is our hours after midnight. So that really means we're talking about military time, right? So how many hours of the day will the temperature be above 55 degrees? Maybe we're trying to plant a garden. Maybe we're just trying to figure out how many hours it's going to be warm enough to be outside. So, whoops, there's this typo in that. The simplest, not simples, simplest way to think about this is to think about the shape of the graph that describes this function. So this thing is sinusoidal, right? So it looks, I don't know if you can hear him. It looks like this, right? It goes around and around and around, yes? Since we're talking about a day, we know that it actually probably is only part of that. it probably looks like this, right? It warms up and then it cools down. So what have we got? Well, we've got a vertical shift that says that our minimum is at 50, right? We've got a change in period that says that our period is going to be what? Well, it'll be 2 pi divided by pi over 12. So our period is 24 hours. Well, that makes sense. Yeah? Yeah. So this is probably actually going to do this, isn't it? Yes. So that means that our period here will be 24 hours. So we'll do this, move this over to here so we start at the x-axis. Right? And what else do we know? That's really all we need to know in order to solve this problem. So what I've done is I've moved the 50. So what we're really doing here is we're solving the equation. So what we care about, so this is 55. We're trying to figure out how many hours this represents. So remember my x-axis is time. So we can find these 2 points and then find the distance between them in order to solve this problem. So what I've got is 55 equals -10 times the sine of pi over 12 times h plus 50. Subtract 50 from both sides, and we get 5 equals -10 times the sine of pi over 12 times h. Again, we're trying to isolate that trig function, so let's divide by -10, and we get -1/2 equals the sine of pi over 12h. Okay, think about our unit circle. What angle has sine of -1/2? 11 pi over 6 and 7 pi over 6. We're going to go with radians because our formula has got pi in it. So what we have now is that pi over 12 times h equals 11 pi over 6. Or pi over 12h equals 7 pi over 6. Solve these equations for h and we get that h equals 22 or 14. So 22 hours after midnight, that is 10 p.m. 14 hours after midnight is 2 p.m. So between 14 and 22, our temperature is above 50, so that's a total of 8 hours that our temperature will be above 55 degrees. What we are doing here without saying it is using the inverse functions. The inverse function is shorthand notation for what angle has sine, cosine, tangent, whatever we're looking for, greater than, equal to, whatever we said. So we write inverse functions either as arc functions, or sometimes you'll see this just as a tan, or a cos, and there's always a number, or a sine. This is just shorthand for arc. Arc just means inverse. More frequently, oh, there's another typo. That should be subscript, not subscript. More frequently, especially in mathematical applications, you'll see a subscript -1. This is pretty standard for an inverse anytime you're using function notation. So don't say sine to the -1, say inverse sine or arc sine of theta equals 1/2. This is the same thing as saying what angle has sine of 1/2. Notice that the output of the inverse trigonometric functions are angles. Okay, so you've probably already thought to yourself, okay, wait a minute. Sine and cosine are periodic functions. If I think about their inverses, that means their inverses aren't going to be functions. And that's true, because the inverse would fail the vertical line test, right? What we do in order to handle that is we restrict ourselves. So we restrict the sine to -π/2 to π/2. So what that means in terms of our unit circle is that when we are working with inverse sine, we are restricting ourselves to only the positive x-axis. So when we're working with sine, inverse sine, we are only talking about this portion. Sorry. Yes, that's correct. This portion of the unit circle. So positive x-axis. In other words, yes. On this region, inverse sine will be a function. When we are working with inverse cosine, we restrict ourselves to the positive y-axis, so between 0 and pi. And we use the same restrictions for tangent as we do for sine. This then impacts our domains. The domain of inverse sine is, well, both domain and cosine have got both sine and cosine have domains of -1 to 1. But it impacts their ranges, because remember that the range of the inverse is the same as the domain of the native function. So the range of inverse sine is -π/2 to pi/2. The range of cosine, inverse cosine, is 0 to pi. And the range of tangent is -π/2 to pi/2. So let's do some of these. The inverse sine of √3/2. Take a look at your unit circle if you need to. What angle has got inverse sine √3/2? And remember what we restrict our sine to. Sine is restricted to the positive x-axis, right? So on that positive x-axis, only 30 degrees has got a sine of, only 60 degrees has got a sine of √3/2. Right? Or, what is that in radians? Pi/3. Okay. How do we find the inverse sine of -1/2? Again, consult our unit circle. Inverse sine of -1/2 is 330 degrees. Or more often we'll write that as -30 degrees. Yeah. Or that is negative pi over 6 radians. Okay, what angle has cosine square root 2 over 2? That's 40 degrees. Oops, 45 degrees, sorry. Or pi over 4 radians. Okay, what angle has cosine negative 1/2? So remember, cosine has got a different restriction. We use a different region for cosine so that we only have one answer. We use this region for cosine. And we're looking for the angle in this region that has cosine of negative 1/2, and that will be 120 degrees or 2 pi over 3. Hmm. 120 degrees or 2 pi over 3 radians. Okay? Inverse trigonometric functions. The output is the angle. So let's do an example. And this one takes a little thinking, so I'm going to walk you through the thinking. So we're going to go back to our London Eye Ferris wheel. It's got a radius of 67.5 meters, and it's centered 69.5 meters off the ground and completes 1 revolution every 30 minutes. How long is a rider above 100 meters? So, in other words, how long do you have to be 100 meters above the ground? Okay, so what we need to remember is that we can use the sine function to describe the height of a rider over time. And we could go through and figure out the vertical shift, but realistically, since we're just trying to solve the time question, it's easier to redefine our axis system so that the center of the eye is the origin. So that changes our question a little bit. What we're going to do is we're going to say, well, okay, I'm going to make the center of the eye be the origin because that simplifies my life. So what that means then is I'm looking for how long is the rider's chair 30.5 meters above the horizontal line defined by the center of the origin of the eye. And we can do that, but what we need to remember is we can scale our circles by their radius. So we want to turn our big 30.5 meter circle into a unit circle. We do that by ratioing. So what we're really looking for is what angles will give us a y-coordinate of 30.5 divided by 67.5, which is 0.45185. So this is y equals 0.45185 meters above the center of the eye. So all I've got here is I've just got a unit circle. And I've just drawn the 2 points that we care about, and what we're trying to find is this angle. Once we find this one, then we can find the other one, right? But since we're working with sine, we know we got to find this one first. So what we're saying is, what angle theta has sine equal to 0.45185. Let's solve that. All right, we're going to use our calculators to solve this one. And the only thing we got to be careful with on our calculators is we need to check our mode so that we know whether it is giving us radians or degrees. So let's go into our mode. Mine is currently set in degrees. We can do this in either. My brain thinks better in degrees, so let's go ahead and do it in degrees. So what we're going to do, so in degrees, I'm expecting an answer between negative 90 and positive 90. And actually, I'm expecting an answer between 0 and 90. So if you've got a TI, you type second inverse sine and then put in 0.45185 and hit enter. And we get an answer of 26.86 degrees. But what I really care about is how long is it going to take me to go from here to here, right? Well, so what we need to know is how many degrees I have in here. And I get that by realizing that this total is 180. So I can take 180 minus, and I've got 26.8 on this side and 26.8 on this side. So that's 2 times 26.86. And I get 126.28 degrees. I'm not quite done yet, am I? Because I want time. So let's talk about my angular velocity. We said that we make one full rotation, 360 degrees, every 30 minutes. That means we're moving at 120 degrees. Sorry, that's not right. 12 degrees per minute. All right, let's check that. 360 divided by 30, 12 degrees per minute. Yes, we're going to travel 126.28 degrees. So divide that by 12 degrees per minute. And we find that for 10.5 minutes, we're going to be above 100 meters. Okay? There's a couple more things I want to do with you before we go. And for that, I need to end my slideshow for a second because I forgot to unhide my slides, which does not help. But these are some important things to practice, so bear with me for a second. And we will go back to our slideshow. There we go. So I hope that London Eye example made sense to you. The thing you need to be careful of is realizing we're only working with half of the circle when we're doing those calculator problems. Let's play some games with sine, cosine, and inverse sine and inverse cosine. What I want to do is I want to find the inverse sine of the cosine of 11 pi over 6 degrees. So what I am saying here is what angle has a sine that is equal to the cosine of 11 pi over 6? Well, let's take 11 pi over 6. That sounds familiar, right? So let's take a look at my unit circle. My unit circle says that at 11 pi over 6, my cosine is root 3 over 2, and my sine is negative 1/2. So what I'm actually saying is I want the sine inverse of, what was my cosine of 11 pi over 6? Root 3 over 2, right? So what angle has a sine that is equal to root 3 over 2? Sine, remember, is y-coordinate, so 60 degrees. Okay? Or what? Pi over 3 radians. So what I did was I simplified the inner function first, and then I applied the outer function. There are different ways to do this. So 12/13 isn't an angle that we recognize, right? So let's take a look at the cosine, how to find the cosine of the inverse sine of 12/13. So inverse sine, that means what angle has sine of 12/13? Well, let's draw a triangle here. Sorry, my skills are not so good. Let's see if I can make this better. Oops. Oh, now comes the hard part. All right, not too bad. I used to have, I may have to find my drafting triangles because that would work really slick. Okay, so let's think about this. Sine. Remember my favorite vacation spot? So, So if an angle has a sine of 12/13, say this is my angle, that means the side opposite divided by the hypotenuse is equal to the sine. So what I just did was I realized that this angle theta is the angle whose sine is 12/13. Why do we care? Why would I do that? Well, because now I can find this side length down here, right? This side length is, so let's call this A. A is the square root of 13 squared minus 12 squared. So let's take out our calculator. Turn this back on. 13 squared, 13 squared minus 12 squared is 25. I know the square root of 25 is 5, right? Let's check that. What's 25 plus 144? And let's take the, square root of 169? Yes. So this side length down here is 5. So now what is the cosine of this same angle? Because that's what this is asking for. I just found that I just drew, I don't really care what that angle is, right? Remember that the output of an inverse sine is going to be an angle. But I don't really care what that angle is. What I care is, what's the cosine of that angle? Well, this is the triangle that gives us all my side lengths. So this angle theta, will have sine of 12 over 13. So now I can use my triangle to find the cosine of that angle, and that's going to be 5 over 13. Okay? There are probably other ways to do it. This is the way that makes the most sense in my head. All right. We can do the same thing with tangent. So again, let's draw a triangle. And I'm not going to try to be fancy this time. I'm just going to draw a triangle. Okay? The sine of this angle theta is 3 over 7. Yeah? Okay? That means this is going to be square root 40 or 2 square root 10. Everybody know how I got that? I took 7 squared, subtracted 3 squared, which is 49 minus 9. You take the square root. Square root 40, simplify that. That's square root of 4 times the square root of 10, so 2 square root 10. What is the tangent? Tangent's the opposite side over the adjacent side. So that will be 3 over 2 square root 10, or if we rationalize our denominator, that's going to be 3 square root 10 over 20. Okay? The output of the inverse sine is an angle. But we don't really care because what we want is the tangent. So the tangent of the angle whose sine is 3/7 is 3 root 10 over 20. All right. Now this is the end of my, almost. Let's do this one. This one's kind of interesting. Because I don't have a number, do I? What do I have? I have a tangent of 3x. Okay, well this is my angle. So this is what will come out of the tangent. The tangent, remember my favorite vacation spot, SOHCAHTOA, the tangent of an angle is the opposite over the adjacent. 3x is 3x over 1. We can do that. Now I can find c squared equals 3x squared plus 1. So c is going to be the square root of 9x squared plus 1. Yes? Yes. So the cosine of that angle is the adjacent over the hypotenuse. So that's going to be 1 over square root 9x squared plus 1. Okay? All right, that's it for today. Have a great rest of your day. Do good math, and I will talk to you all soon. I am going to schedule a web conference, a couple of them, so check the Canvas website for scheduled conferences. Let me show you where to find those. So let me give you back my screen. And And let me just end this. Wait. Make that go away. Yeah, I want to save that. And let's go to our Canvas site. Our math class. And look here in conferences. I don't have them scheduled yet, but I will schedule a couple of different options next week. So, and well, let me just do it now. So I will be online for 60 minutes. Okay, never mind. I will schedule something for Tuesday afternoon and Wednesday evening of next week so that we can meet together and I can answer any questions that you might have in a one-on-one environment. Well, maybe not one-on-one, but definitely real time, which is better than this delayed thing. So look in the conferences for something scheduled, and I will see you all soon. In the meantime, do good math and have fun.